So, hello everyone. I'm happy to welcome all of you to our, I hope my counting is right, 51st edition in the virtual seminar series on precision physics and fundamental symmetries. It is the first seminar after the summer break with an outstanding speaker right at the beginning. My name is Klaus Blaum from the Max Planck Institute for Nuclear Physics in Heidelberg, and it's my great pleasure to introduce our today's speaker, Professor Reinhard Genzel from the Max Planck Institute for Extraterrestrial Physics, professor at the Ludwig Maximilian University in Munich, and emeritus professor at the University of California in Berkeley. To be honest, it's almost impossible to honor sufficiently enough the scientific merits of Professor Genzel in a 2 minutes introduction. There is not a single prestigious award that has not been given to Reinhard for his outstanding astrophysical discoveries. Among others, the Leibniz Award, the Stern-Gerlach Medal of the German Physical Society, the Balzan Prize, the Prague Prize by the European Astronomical Society, and of course the most prominent one. Most recently, Reinhard received the Nobel Prize in Physics in 2020 for the discovery of a supermassive compact object at the center of our galaxy. As a private note, what is most amazing to me with Reinhard is that although his calendar must be overbooked by at least a factor of 3 or so, he still serves a lot for the Max Planck Society in several committees, foremost to support young scientists. So I think that's really something that's very close to his heart, to support young scientists in the field as much as possible. Notably, it was during a W2 hiring committee which Reinhard and I attended when he received the important call from Stockholm. Reinhard for sure still remembers. And then he only typed me in, Klaus, I have to leave, watch the TV at 12 o'clock. And so that was really very nice. It's our great pleasure and honor that you, Reinhard, accepted our invitation to talk about galaxies and massive black holes and explain us how precision measurements on astronomical scales allow to test general relativity. To the audience, as usual, in case you have questions, please type them into the chat room or the question and answer box. We will address them at the end of the talk. So Reinhard, we are looking forward to your presentation and the floor is yours.
Well, Klaus, thank you very much. So let me try to share my presentation. Right, so the topic of this talk has several floors, if you like. There is astrophysics and the issue of the galaxies and their formation and evolution. The second floor in this talk is the issue of the paradigm that most, if not all, of the galaxies you see on this deep image with the Hubble Space Telescope, distant galaxies, have in their centers a massive black hole of millions to billions of solar masses. And the third floor is physics, namely to then use actually, and you will see how we do this, the nearest of these galaxies, namely our own, to actually, like in a laboratory, test general relativity in a regime where it has never been tested so far. So I'm an astrophysicist, I'm an astronomer, but also I'm an experimental physicist, and I will try in this talk to give you a little taste of how we've done this. If I say we, this of course is not a type of research you do by yourself. It's also not a type of research which happens overnight. In my case, it took about 40 years to get where we are now, and I'm trying to describe to you how that happened. There are many young people involved, and since Klaus already mentioned the Max Planck Society, the Max Planck Society in so many ways has been like a paradise because it has given us as experimentalists the opportunity to take risks, to be independent of colleagues who might say, oh, this is not going to work, don't do it. We just could go ahead and, much of the time, our risk-taking actually did pay off. Now, as an introduction, of course, let me remind you of the overall picture and the fact that general relativity is now a little over 100 years old. Yet it is still one of the most vibrant research fields because, of course, many parts of general relativity are either not yet fully tested or there are new aspects to the theory. For instance, the issue of dark energy, for instance, the issue of the Big Bang, for instance, the issue of the fate of information, which may or may not be preserved in black holes as material falls into them. All of this is subject of current research, and in fact, a number of research papers on general relativity in black holes is almost exponentially increasing after 100 years. Of course, you know that Albert Einstein's theory, already 1 year after he talked to the Prussian Academy in 1915, found the first solution, which Karl Schwarzschild found. And that Schwarzschild solution already had in it, although he didn't say it at the time, the concept of a black hole. Because it basically embodied the fact that photons are the fastest communication we have, and also photons feel gravity, such that if you have a very compact mass and a heavy mass, a mass concentration, then there may be a region where photons cannot escape anymore, and you basically have no relation to the outside world, so no communication to the outside world. That's the concept of a black hole. Roy Kerr in 1963 found a second solution, which is very important, namely that black holes not only have a mass, but also can rotate, have a spin. There's also a solution with charge, but that one, for reasons I don't have time to get into, probably does not have a very important role in astrophysics, because once there is a unipolar charge, in astrophysics, you always have magnetic fields such that charges get basically transported and currents can flow. Now, the question, of course, was whether these solutions, which are highly symmetric, might not be the generalized feature. And many people at the time suspected that these black holes really would not be realized in physics. And Roger Penrose, whom I shared the Nobel Prize with, and Andrea Guess, Roger really wrote very, very clear, insightful papers showing that even if you just look at the general topology of the problem, that you could not avoid that compact masses, once the curvature of space-time was large enough, would take on a black hole solution. But the question, of course, is whether nature actually has realized these things which general relativity predicts. And so it took quite a while until the first possible candidates came into the view. The first ones were X-ray emitting binary objects, which in the 1960s were discovered by the X-ray astronomers, Riccardo Giacconi and others. And we now know that these binary objects, or some of them at least, have what we would call a stellar black hole as one of its members. And so the X-ray emission is hot gas, which is heated up as it falls into the central region of a black hole and outside of its event horizon. The next step, and that's the most important one for this talk, was the discovery of quasars. Radio astronomers, when looking at the sky and finding new objects emitting radio waves, discovered faint optical stars, what were faint optical stars, but bright radio sources. And Martin Schmidt, who used the big Palomar telescope, took a spectrum of one of these objects and found that all the spectral lines in the optical spectrum were redshifted by 16%. Now, most people assume that this redshift is due to the expansion of the universe. And so then you can convert, if you know what the Hubble constant is, what the distance of these objects were. And the first object they found, they then concluded had to be about 2.5 billion light years away from our location, which at the time was a sensation. Nowadays, we know that there are much further such objects, such quasi-stellar radio sources, quasars. But the question, of course, is if it's so far away, then what looks like a meager little star actually produces a lot of energy, a lot of luminosity. In this case, at the time, about 1,000 times more than the entire Milky Way with its 100 billion stars. So how could you possibly produce this much energy? And a number of theorists went to work, and within a decade, a paradigm appeared, which was a bit paradox, namely to say, you could get this much energy if you have a big black hole and you have material falling onto the hole. Now, the material, of course, likely has angular momentum, so it can't fall in straight, but it would form sort of a disk-like structure. And then if there's enough friction, we think it's magnetic friction in the system, then you could transport the angular momentum out and the material would go in. And before the material disappears behind this event horizon, then it would be able to convert the gravitational energy into radiation. And if you look through this theoretically, then it turns out, depending on the spin of the black hole, you can convert between 7% to almost 40% of the rest mass energy of the infalling particles into radiation. So that's 100 times more efficient than fusion. Well, that's a proposal. How would you prove it? How could you prove that this idea is really correct? And I'll come back to this in a moment. So this is 1963. And as you will see in this talk, about 10, 15 years later, the first evidence actually in favor of the paradigm appeared. And from then on, it was a sort of an interesting race to get ever better data. Nowadays, 100 years after the theory was invented, we have three categories of pieces of evidence. The one I will talk about here, which is to use the nearest galaxy, our own, to show that there's an object in there which has about 4 million solar masses and which appears to be a black hole beyond any reasonable doubt at this point. The second piece of evidence is the detection of gravitational waves from in-spiral stellar black holes, from binary black holes. But that emerged also only a few years ago, as you know, when the in-spiraling and then basically the merging of such stellar black holes was seen by the LIGO consortium. And finally, radio astronomers have used the technique we call very long baseline or intercontinental radio interferometry at very short wavelengths to look at nearby, relatively nearby, but very massive black holes. One of them is this object M87, to look at the distribution of radio emission. And what you see there is a bright ring of radio emission, synchrotron emission, surrounding a rather dark spot. That dark spot was predicted many years ago to be characteristic of a black hole because photons, as I explained, see gravity too. So if you illuminate a black hole from behind and you look at it, then within a certain radius, the photons cannot make it to us, but are bent out of the line of sight or even fall into the black hole. So at least qualitatively, this is also a very strong piece of evidence that such black holes occur. So it's remarkable that we are now in an epoch, and that will continue as I will explain to you, where from first speculations from that theory to first evidence, we now have firm experimental evidence, observational evidence for these objects. But for those of you who are not experts, let me just give you a very simple sort of explanation how we actually see black holes. obviously, I made the case that normally, at least, unless you have a lot of accretion, black holes, of course, are objects where light cannot escape. So how do we see them? Well, if you think of the sun as an example, then obviously we know that the surface gravity on the sun means that a rocket which would have to be shot into space would have to have an escape speed of about 600 kilometers per second. On Earth, it's about 11 kilometers per second. Now, this escape speed depends on the mass of the sun and also inversely on the radius of the sun. So in a Gedanken experiment, you could now shrink the sun and the escape speed increases. And if you shrink that size of the sun to a size of only 3 kilometers, then the mathematics tells you that the escape speed is the speed of light. So such an object, if it were 3 kilometers or somewhat smaller, has a communication sphere in the event horizon within which photons can't escape. So there you have your black hole, and the mass of the black hole is proportional to the event horizon size. For the sun, 3 kilometers. For the Earth, it would be 1 centimeter. For the objects which I'm talking about in my talk, it is basically the solar system scales, or it's a little less than the distance between the sun and the Earth, or in very massive black holes, even bigger than that. So suppose we now have such a black hole. How would we be able to see it? Well, the answer is through gravity, through the interaction of the mass of that mass concentration with test particles. Think of the solar system again. Suppose there would be a solar system with a sun in the center, but that sun would be one which doesn't radiate, it's a black hole. Well, the Kepler's laws and the motions of the planets in that system would still be the same as in our own. And Tycho Brahe, measuring the planetary motions in that system, would find the same laws, namely the fact that the inner planets move faster than the outer ones, and the orbital speed is 1 over square root of, proportional to 1 over square root of the distance from the central object. So it's that methodology which most of the experiments are using. We are using particles, either stars or gas particles, or photons, to basically measure the strength of the gravity, thereby measuring the mass. And then if you have high enough angular resolution, also constrain the size of the object by looking at very, very close to the central object. And if you're lucky, we can then exclude anything else but a black hole. So that's sort of the general idea of the experiment. Now, Lindenbell and Rees realized that distant quasars are so far away, at least in the 1960s and 70s, too far away to use stars or gas clouds, resolve them and resolve their motions to realize this experiment, which I just described to you. The objects would have to be much closer. But then they speculated that if quasars are just sort of at the high end, if you like, of the accretors, and that most other galaxies might have black holes, but not accrete that much, then you could look at nearby galaxies and even better, our own galactic center, if you want to see whether there's a central mass there. The center of the galaxy is 27,000 light years away, so that's a factor of about 30,000 closer than the nearest big quasar-like active galactic nucleus. So that is very advantageous. What's not so advantageous in the galaxy is the fact that between us and the center of the Milky Way, there are not only many stars, but also dust, interstellar dust particles, which in fact are the particles together with the gas which form new stars, but they also dampen the visible light. So it's actually not possible to see the very nearby on astronomical scales, nearby galactic center in the optical, You have to go to longer wavelength, infrared, radio waves, etc. But also you can go to shorter wavelengths, X-rays. What you see in front of you is a modern state-of-the-art image with all the technology, which I'll describe to you next, which we now have to make sharp and very, very deep near infrared images. You see there is 1 light year. So what we're looking at is the central few light years around the center of our Milky Way. And that contains an extremely dense star cluster, very bright stars, actually. Some of these stars have masses of 50 to 100 solar masses. And it's very surprising, actually, to see them here. And the radio astronomers have been looking at this region too, and have found that in the center, right there where the dot is a compact radio source. And its size in the millimeter range is as small as 40 microarc seconds. 40 microarc seconds is about 20 centimeters on the moon. And in fact, that's on the scale of the event horizon of a few million solar mass black hole. So once the radio source was found and one had an inkling that there might be such a compact object there, then of course the question indeed is, could it be that here is a massive black hole? So in the 1970s, in Berkeley, Charles Townes and his students used the fact that this central region of high density of stars is surrounded and passed through by streamers of ionized gas, that's the pink stuff, and neutral stars, neutral gas, which is the green stuff. And that, of course, can be looked at with spectroscopy in the infrared, through infrared lines, and you can measure the motions as Doppler motions in the spectra. So Townes, who got his Nobel Prize in the 1960s for the invention of the laser and maser, had turned into an astronomer in later years, and used, of course, his knowledge about infrared spectroscopy, etc., to build, at the time, revolutionary new apparatus to look at the infrared bands in space. He and his students, and I joined them in 1980 as initially a postdoc and later on as a faculty member. We built experiments to then map out the motions of these gas clouds and derive from that the enclosed mass around Sagittarius A star. And what we found by around 1985 was the following. That's shown in the left diagram. If you plot the enclosed mass in logarithmic units as a function of distance from Sag A star, which is the horizontal axis, then you see at large scales, of course, the mass increases. That's the extended mass due to the stars in the center of the Milky Way. But when you come inside of about few light years of Sag A star, then the mass does not change anymore. It gets sort of stuck between 2 to 4 million solar masses. That's what we had at the time. And so we were fully convinced, and Charlie was definitely fairly convinced, this must be a black hole. So that is a confirmation of the prediction of the theoretical work in the 1960s and early 70s. Well, the problem is twofold. Number one, many of our colleagues looking at our results felt that how can you be sure that the gas motions we are seeing really map out gravity? There are magnetic fields in this region, and of course, strong magnetic fields might influence the motions. There's also stars which have winds, and that might push around the gas. So one isn't really very sure that the motions of gas fiducially map out gravity. The more important objection was, well, a few light years is a very compact region astronomically, and certainly hard to observe at the time, but it's a million times the event horizon of a few million solar mass black holes. So who knows? Could be something else. It could be a cluster of neutron stars or faint stars or something like this. Does not have to be a black hole. So that was sort of the general feeling of our colleagues. And it was clear to make progress, one would have to do two things. One is to go to better traces, use stars, which really are surely tracing gravity, and also to smaller scales so that one can exclude other configurations. So let me say a few words about the very important role, of course, of technologies. For those of you who are experimentalists, I think you will understand that this is, of course, the case in many fields, that before you can do ambitious stuff, you better get your apparatus right. The first problem we had to solve at the time was detection, sensing of infrared photons. When we started, we had sort of single detectors, and that's not good enough to basically make images, sharp images of fields of stars. So we wanted to have imaging detectors in the near infrared, around 2 micrometers in wavelength. And that only became available slowly, especially in the US, as a result of work the US military had done. The military then transferred some of the technology after the end of the Cold War to the civil sector. In fact, Charlie Towns was very, very essential in that, because he knew many of the people in government and told them, look, astronomers could benefit a lot. So by the early 90s, such detectors became available to astronomy and also improved, made larger, made less noise, and so forth. Nowadays, we astronomers, together with small companies, build our own detectors, but at the time, we really benefited a lot from the military developments. The next big step is adaptive optics. If you are on the ground and you observe a distant star, then of course the waves, the wave fronts from the star have to pass through a refractive and turbulent atmosphere, which bend the waves and distort the images so that they become unsharp. Now, of course, you can put a telescope in space, but that is by nature fairly small. The Hubble telescope is only 2.5 meters. The technical solution nowadays is to use adaptive optics. You sense the wave fronts, you measure how they deviate from a straight path, and then you have a deformable mirror in the optical path to correct for that. So that allows you then to really unbend the waves and get from a big spot of seeing limited imaging to a diffraction limited image. And so that allows you to, in fact, make sharp images on the diffraction scale of big 10-meter class telescopes, which came into operations also in the 1990s. So with these two technologies, we could improve the sharpness of images by factors around a factor of 20 or 30 and really get sharp images. Now, you do need to analyze the light, and for that, you need a bright star. And often enough, you don't have a bright star. So another technology we had to develop are artificial stars. That is done by shooting lasers, most frequently using sodium D, and focusing these lasers up at 90 kilometers in the upper atmosphere. The Earth's atmosphere is exposed to meteorites. Meteorites enter the atmosphere, get destroyed, and rain material down. And there's some amount of sodium in these meteorites. So around 90 kilometers, there's a layer of a few kilometers of enhanced sodium. And so we focus the laser at that altitude, make a spot, and use resonant backscattering of the photons to generate an artificial star, which then goes back through the atmosphere, senses the distortions, and can be analyzed. And you can make the brightness of the star almost any brightness you like. So that really is a very, very powerful technique. So that gives you a bit of a feeling what has had to happen. Bigger telescopes, low noise detectors, adaptive optics, of course, fast computers. There's also a technique called integral field spectroscopy, where you don't get only spectra from a single point, but from an entire field. So all these techniques helped to improve things. Now we are only at the beginning of a new revolution, which will come in the next few years, and where we at MPE are intensely involved in, and that is another generation of telescopes, which is still bigger. The biggest telescopes now, like the VLT of the European Southern Observatory, which you will see later we are using, are 8 to 10 meters in size. This guy, also to be put down in Chile in the Atacama Desert, as we speak, will have a size of almost 40 meters. And in fact, here, adaptive optics with multiple laser beacons is almost the only way to operate this thing in a good way. So dark skies is not what we are using anymore. There's no more romantic looking into the dark skies. You're really using bright lasers to be able to make sharp images. Our institute is the PI Institute for the First Light Camera on this fantastic new machine, which we hope will go into operation in about 5 years or so from now, just at the end of my personal career as a director. Okay, so with these kinds of techniques applied in the beginning in the 1990s, we then started to look at the Galactic Center, initially with a smaller telescope of ESOs, 3.5 meter telescopes, to look at the motions of stars. At the same time, another group at UCLA, using the new Keck telescopes, 10-meter telescope on Mauna Kea, Andrea Guess, with her colleagues Mark Morris and Eric Becklin, started doing same kind of an experiment independently. So after a few years, we had our first results, which you see now on this image in the following way. What you see there in colors, red, green, and blue, are 3 different years, 1 year after the other. And you can see that there is a green-yellow cross. That's the position of Sagittarius A star, the radio source. And the circle gives you a light month. So we're now really on very small scales, which we can do with this adaptive optics type techniques. And we see that there are stars close to Sag A star, which move very fast from year to year to year, which is basically making a prism effect on this superposition. And if you look up at the upper right, you see that the motion of this one star is about 2,000 kilometers per second. That's tremendous. That had never been seen before when we discovered that. 2,000 kilometers per second is 100 times as fast as the Earth around the sun. And at the distance you are there from the radio source, you can use Newton's laws to immediately calculate sort of a first order mass, v squared, velocity squared, times the distance over g. And what you find is a few million solar masses. So that's the same mass we had seen with these gas clouds, but now with a better tracer and on smaller scales. You can also qualitatively see actually that this is a compact mass, because Kepler's laws, as I mentioned, tell you that the velocity of orbital motion go like 1/square root of distance. So the further stars don't move as fast. And indeed, if you look here in the image, the outer stars are almost white. So their motions are much smaller than the central stars. So we had confirmed by the mid-90s that there was indeed a mass concentration of a few million solar masses, now without any doubt. But must it be a black hole? Now we were closer in, so indeed we were now on a scale of about 100,000 times the Schwarzschild radius, but still you could think of configurations other than the black hole, which might mimic these observations. So how could you do better? Well, if you would dream, and if nature would give you what you wanted, you would like to have stars which come very, very close. And stars for which you not only can measure statistically the velocities, but actually their orbits, so that you can, from these orbits, make precision measurements of the central enclosed mass. And nature was nice to us. It gave us such stars, although nobody expected it at the time. And I'll come back to this aspect a little later. And so we were able to see in 2002, one star go around a pericenter approach around Sagittarius star, which was a mere 17 light hours, very highly elliptical orbit. And the motion of that star in 2002 was about 7,500 kilometers per second. At 17 light hours, that's again a few million solar masses. So now we know that the mass concentration of these few million solar masses is really truly on planetary scales, because 17 light hours is about 4 times the orbital radius of our planet Neptune around the sun. So this is really remarkable. 27,000 light years away, we can see a star moving around a point which produces dim radio emission, but about that. And that seems to have a large mass. You also see that the experiments of the UCLA group in red and our data in blue agree in very, very good agreement. So clearly, there's no doubt about the data and the interpretation. So by 2002, most everyone in astronomy and some physicists started to believe that this was actually indeed a fairly believable and certainly at the time the best piece of evidence for the existence of these massive black holes. But again, let me ask, must it be? Could it be not still something else? There were some speculative configurations, like a so-called boson star, which would be very compact, would fit in there, but not a black hole. Also, we have to assume to interpret the data that general relativity is correct in these extreme environments, and nobody had tested general relativity. So that obviously we knew in the mid-2000s would be the next challenge. Test general relativity when the star would come again, because the stellar orbital period is about 16 years. So we knew that star, which we had seen, will do the same motion 16 years later in 2018. And then we have to be ready to measure still better. In the meantime, both groups started to look at other stars in the field, also moving very fast, and began to delineate their motions. And that brought up another riddle, which is very interesting, which is the so-called paradox of youth. Let me explain what I mean by that. So we found more orbits, many highly elliptical orbits, also many coming very close to the galactic center. And as one goes further out, however, these very random orbits all of a sudden seem to become more regular and form sort of a disk-like configuration. You see the outermost orbits are more in a plane, while the inner ones are in all different directions. So how could you actually imagine that these stars got in here? The simplest explanation that basically the interaction, the two-body gravity interaction between stars, that stars move from the outer nucleus into the inner nucleus, that doesn't work because it takes too long. It takes about 10 billions of years for a star to move in, whilst these stars we're looking at here are only a few million years old. So that's really a riddle. What we think nowadays, what happens is that the innermost stars, which we're using to trace the central black hole, actually were members of a binary stellar system, which sort of happened to be on an almost radial orbit, and then got destroyed by the three-body interaction of the big black hole with the binary, whilst the stars in this plane actually formed there when the gas cloud fell in a few million years ago and got dense enough that it overcame the tidal forces of the black hole. I don't want to say more about this, but that tells you that actually this scientific issue here is broader than just the black hole and general relativity. It is also about, exploring the universe and seeing the fantastic things nature does sometimes in our universe. So 16 years later, what could we do better? Well, I've grown up in radio astronomy, and in radio astronomy, if you want to have higher angular resolution than a single telescope provides, what you can do is interferometry. You basically bring the light together coherently from different telescopes and then interfere it, and then you get the resolution of the distance between telescopes, not just the size of a single telescope. Now that is standard methodology in radio waves, but is exceedingly difficult at optical. For once, because the wavelengths are so much shorter, also because the Earth's atmosphere has a very short coherence time in the optical of only about a millisecond. So everything is very, very fast. There's vibrations of the telescopes, et cetera, et cetera. So when we proposed to the European Southern Observatory in 2005 to build an interferometric combination of the 4 8-meter telescopes, many people were very skeptical that this could work. We called that gravity, and Frank Eisenhower in our group, a genius of an experimentalist, and a European team, including ESO, built that instrument in the next 10 years. And we were actually ready in time for the Parry of S2. But before we look at that and the science which has come out of that, I wanted to show you how complicated an instrument that is. So we made a little movie. We call that the last millisecond of the tortured photon. And you will see why that is. So basically, we have 4 telescopes, and here's our light beam coming at one of these telescopes. There's the Atacama Desert. There's one of the 8-meter class telescopes, primary, secondary, and tertiary. And now the light beams have to be diverted down into the basement of the telescope to a tunnel where we can direct the light in a joint beam. So there's many mirrors. The next thing we have to do is we have to use adaptive optics. So we have to analyze the light beams. That's the adaptive optics system here, which was built at the Max Planck Institute for Astronomy in Heidelberg. And then we bring the light from all the 4 telescopes together in a tunnel. We actually correct for the optical path length differences here. And then finally bring it together, the 4 beams from the 4 telescopes in a cryogenic environment where there is no more thermal noise and no more vibrations. Now the beams have to be prepared here. So there's lots of mirrors, and basically we have to pick exactly the spot on the sky. So there's an optics arrangement. We have to make sure that all the telescopes are properly aligned. For this, we shoot laser beams back through the system towards the telescopes. But finally, then we have 4 beams from a spot on the sky, which we want to interfere now. To do this efficiently, what we do is we bring the light from open optics into single mode fibers, because that's very convenient. So now we're in single mode fibers. Here we can actually use these fibers by pulling and pushing on them to correct for residual path length differences, which we can test for by using a second star on the sky. We can also align polarizations here in the single mode fibers. And finally, then the 4 beams are coming together. Now we have to interfere them. And we do this very much like in radio astronomy in a little chip borrowed from the technologies in communication industry, where we have basically a coherent combination of all the 4 beams into the different telescopes. So 6 different combinations, samplings at 4 different path lengths, so 24 outputs. And then finally, we pass all of this through a spectrometer to disperse the light so that we can really see exactly the fringes on the instrument. You can imagine that technically this is quite challenging, and it was a fantastic team which really put this together. So having this new machine called gravity, which is unique in the world, what can we do with it? Well, gravity, by having a largest separation between telescopes of 130 meters, improves the angular resolution of the measurements of a single telescope by another factor of almost 20 to about 3 milliarc seconds. And then we can measure the positions of stars to about 50 microarc seconds. That's about a euro cent coin on the moon. And so with that, we can make very, very sharp and detailed observations of the stars in the center. So let me summarize this for you. When we started 40 years ago, we were barely able, because of the detectors, to get infrared images. And that's what we got, sort of smeared, but reasonably interesting images at seeing limited resolution of a 4-meter class telescopes. Then, as I explained to you, the adaptive optics and going to 8-meter telescopes improved everything by more than a factor of 10 to the right upper image. Now we see many of tens of stars and also very faint stars. And indeed also the black hole in the very center of the image, you see a very faint smudge. That's Sagittarius star itself in the infrared. So obviously there's hot gas, very hot gas, which produces infrared synchrotron radiation. It's polarized, in fact, and tells us that magnetic fields are very, very strong. And then with gravity, we can look at this little square in the center there, still with higher resolution, to get the image in the bottom right. And to your surprise, and our surprise, this is an image from this year. You don't only see Sagittarius star, and then maybe a star every few years. No, you see, it's like New York Times in New York at night in a busy crossing. Lots of stars, very faint stars, but lots of stars on scales of solar system zipping through there. And if you wait only a day or two, you can see the motions with Sagittarius, with the interferometer, and over a few months, you can clearly see the motions of all these stars, as you see in the bottom left, with velocities up to about 8,000 kilometers per second. So that's the technology which we have from observing the star cluster on large scales and getting a good reading of the central mass. We are now looking at stars which are going around Perry on scales of about 80 times the Earth Sun distance, and moving there with many thousands of kilometers per second. This year alone, we had 4 such Perry passages. And then we can see the motions from night to night, which you see here as different red points, and get very precise registration of the orbital parameters, make fits for the orbital data, as well as derive the gravitational potential. And we can begin to look for effects of general relativity. The first such effect which we were hoping to see is the so-called gravitational red shift. And that is, if a photon, if a star goes through this central region, then the photons have to come from the potential near the mass to us, and thereby lose energy. They get red shifted. That's a very small effect in the case of S2, only about 6 × 10⁻⁴. But with the accuracy of the measurements we have, we can see this as residual differences between the overall orbital motion in velocity space, which you see on the upper right, and then subtracting the Newtonian orbit near Perry, which is near the maximum of the velocity. And then you see that the Newtonian orbit in gray would be just a horizontal line, and GR predicts the red line, and the data are obviously following general relativity. So it's very clear this experiment tells us that GR on this first post-Newtonian effect is clearly obeyed at the level of about 25 sigma. So it's a very significant detection. The next effect in general relativity is the so-called relativistic precession. We know from Newton that if you have a central mass dominating the orbit of another mass, orbiting it in a bound elliptical orbit, then this second orbit, this elliptical orbit or a circular orbit, stays constant in space. But that's not the case in general relativity. In general relativity, there is an in-plane prograde precession for the star S2. That's about 12 arc minutes per 16 years. It's a small effect, but you can actually measure it, as you see on the right side. What you see there again is the residuals from the Newtonian orbit, which is the horizontal gray line in one of the coordinates, in this case, the x coordinate. And at Apo, at the largest distance, where the orbit does not precess very much, you have these red data points. We null the phase of the orbit there. And then basically, as soon as the orbit comes close to the Perry distance, which is 2018, then it rotates very quickly. It's almost like a kink. And general relativity then predicts that this kink leads to a maximum displacement of a few milliarcseconds on the right side in this red curve. And as you see, the data clearly follow this very nicely. Another way to see this is to look at the star S2 now relative to the positions 16 years ago. The measurements from now are the dark blue points in the upper right plot, while the measurements 16 years ago are the open blue measurements. Of course, back then we didn't have interferometry, so they're not as precise, but you clearly see this shift of the orbit, the precession of the orbit to the right. So it's exactly how general relativity predicts the Schwarzschild precession. Now that's a very important effect, not only for testing general relativity, but also to get a statement on any extended mass. Because if there were any extended mass, then Newtonian physics predicts a retrograde precession. So in the general case of an extended mass and general relativity, you would see a combination of the GR prograde precession and then the retrograde precession from Newton, and we don't see such any sign for a retrograde precession. But that's very important also. And then finally, we can see these flares, as I mentioned to you. Sometimes every few days, the Galactic Center becomes very bright, and for about an hour or two becomes very bright in the infrared. And when we look at with the interferometer at these bright spots near Sagittarius star, and we see that they actually are moving around the position of Sagittarius star, as you see in the upper left plot there, with a speed of about a third the speed of light at about 10 times the event horizon size. So here we are now really very close in the relativistic regime, and that's exactly what you would expect if you had a bright spot, say a reconnection zone in a dense magnetic field or very hot gas orbiting the black hole. The radio astronomers also find very compact emissions in air. So that is, so to speak, the innermost relativistic zone, which you would expect in a magnetized accretion zone around a massive black hole. So summarizing, 40 years after we started, what we have done is to basically go from the scale of a few light years, where we saw the first indications that there was a compact mass, ever more in with ever better resolution, better test particles, and now finally looking at the Sagittarius star itself. And when we look at the mass distribution, what we find is that the mass out to about a light year or so is completely dominated by a point mass of 4 million solar masses. Any extended mass is a very, very small amount. A few stellar black holes could fit in there near the orbit of S2, but not much more. By the way, any dark matter you might expect to have congregated there and form a cusp of dark matter around the black hole also doesn't amount to much mass. I mean, we're talking about a few thousand solar masses, so about 0.1% of the mass of the big black hole. So that is not a large contribution. So the paradigm of a big black hole is qualitatively and quantitatively confirmed with these different measurements, as is, by the way, the equivalence principle. I didn't talk about that. And all the way inwards to a few times the event horizon size. What's missing at this point is any information on the spin. That we still need to do because clearly we expect the black hole to rotate, but we don't know how fast. And we would like to know that. And again, for that, we would like to detect the lens steering position of a stellar orbit, but that cannot be done with the stars we're seeing right now. They would have to be still further in. What we can do, though, is, as I expressed, is to exclude any other mass in there. In particular, for instance, also intermediate mass black holes, which many people expect to have formed near massive black holes, sunk into the central region, and then basically orbit around the big black hole. In the Galactic Center, this appears to be a single big black hole, maybe with a few stellar black holes surrounding it. Finishing, let me say 2 words about the cosmic evolution, which I started with. I told you then that we have evidence that distant black holes exist in almost every galaxy. We can measure black hole masses, or at least the masses of the central concentrations in nearby galaxies. And we find that the mass of these central concentrations and the mass of the galaxy, or at least the bulges of galaxies, are roughly proportional to each other. It appears that nature has made about 0.1 or 0.2% of the galaxy mass into a central black hole, at least in the local environment where we can make these kinds of tests. As we go back in time, we can measure the activity of the formation of galaxies as well as the activity of quasars. So we are now on the right side of the diagram, and the Big Bang is on the left side. And when we go back in time, about 10 billion years ago, the Milky Way would have produced many more stars than now, about 100 stars per year. Now it's producing about 2 stars per year. And we think that's because much more gas was accreting onto the galaxies at that time, because the universe was still fairly compact and gas richer than it is now. Quasars were also more common, the red curve. So in fact, quasars, black holes, and accretion and star formation were, so to speak, symbiotic effects happening at the same time. Indeed, we can go one step further. The quasar density in very massive galaxies at that epoch was so high that quasars were actually important to stop the growth of very massive galaxies. So we are beginning to sort of get a view that big black holes actually had a very important role in the evolution of galactic systems from the earliest times. What we don't know is when this all started. Were the black holes first, or were galaxies first? That requires measurements at still higher redshift, which we hope to get for once with that big telescope, which I showed you, the ELT of ESO, and hopefully I can still be active to see some of the measurements of this time. And the Americans are hopefully launching a space telescope, the James Webb Telescope, which also is geared toward measurements of this epoch. So it turns out that the evolution of these black holes, the measurement of these black holes, has been a terribly exciting story for us, for the gravitational wave community, for the radio astronomers. And of course, we can ask, are we done? This is the last time I'm asking that question. And the answer, no, we are not done, because while we have, all of us at this point, shown that the data are consistent with these Kerr-Schwarzschild black holes, we have not shown a very important basic theorem of general relativity, namely that the spin A and the mass m are the only quantities you need to have in order to describe all other parameters of the black hole. So for instance, the quadrupole moment Q of the black hole. This statement is often called the no-hair theorem, and that means that this little nuisance parameter epsilon, which is unitless, is zero in general relativity. Now, from the current measurements of our data and LIGO, we know that epsilon in those cases where we've measured it is on the order of epsilon of 0.3 to 1. With gravity and EHT measurements, the radio measurements combined, we could push that probably down by another factor of a few. Would there be a pulsar near a massive black hole? Because of the terrific measurement accuracy of pulsars, one could push another factor of 2. But eventually, the most exciting experiment, in my view, is going to be the space experiment LISA of the European Space Agency, which intends to measure gravitational waves in space with a gravitational wave antenna of 3 satellites spaced by about 2 million kilometers per second, and measuring low frequency gravitational waves from big black holes. Then one could watch the in-spiral of a stellar black hole into a massive black hole with exquisite precision. Our sister Max Planck Institute, the Albert Einstein Institute, is involved in a leading fashion. In this experiment, my colleague Carsten Danzmann and his colleagues, I really wish my colleagues that they will be able in about 15, 20 years' time to carry out this experiment and then close the chapter, hopefully, or not, of general relativity tests in this most extreme environment. I thank you very much for your attention and listening to me.